So you've read the chapter in the Swift ebook on automatic reference counting, and you already know that every strong reference increments an object's reference count by 1, and that an object's memory is freed once its reference count falls to 0. So we'll create a demo class that prints out its events to the debug area. The dinit method gets called after the reference count hits 0, and before memory is freed. For many classes, you won't need to write a dinit method, because stored properties are automatically released. We're going to use it to see exactly when objects get freed. Here's a simple example which places an object in a reference. In the debug area, we read some class init. This means that our init event was recorded, but there's no dinit. To get that, we would have to cause the reference count to hit 0 by setting the only reference to nil. And now in the debug area, we see both the init and the dinit. Let's see how this works inside of a function. In the debug area, we read called do something, init, leave do something, dinit. See the sum class dinit at the end after leave do something? That means when the scope of do something ended, the reference count of our object decremented to 0 and the instance was freed. However, if that reference had been weak, then dinit happens before the function leaves. A weak reference in Swift is very weak. In fact, the object doesn't even survive to the next line. Here we see the nil before leave do something. That's because the weak reference does not increment the reference count. With 0 references, the sum class instance is immediately freed. So we've been looking at the reference counting as a time-based problem when objects are freed. But the primary advantage of automatic reference counting is that it transforms that into a graph problem. So what is the problem exactly? The one potential downfall of reference counting is the retain cycle. No dinit in the debug area. Since each object is owned by the other, neither one will reach a 0 ref count, so neither will ever dinit, thus never releasing the other object. This is called a retain cycle. It's how memory leaks. Garbage collection in other languages, like JavaScript, would catch this. Garbage collection is constantly trying to solve this problem, meaning the end user literally pays for it in an ongoing way. Arc expects you, the developer, to solve this once, so your users don't have to. We break retain cycles with the judicious use of weak references. In this case, I make another instance reference weak, and the dinits happen. So now the question is, how does the developer know which references should be strong and which should be weak? Think of every object in your app as a tree of objects, with your application at the root. All of these owning or parent objects should hold strong references to objects they need to hang around to get the jobs done. The owned or child objects should never keep a strong reference to their parents for longer than a function call. That would create retain cycles. Member references to parents should always be weak. Next is what trips people up: sibling references. Many developers accidentally use strong references for siblings. It is slightly less code, by the way. This node class correctly strongly references its children and weakly references its parent. But adding strong sibling references means we create retain cycles. While theoretically any node could calculate its siblings by querying the parent, sometimes our class simply won't have that much knowledge of the parent and so needs the reference directly. Sibling references are properly weak. This does add a little extra code because you'll need to write guard let in every function which references them, but this is the only way to write safe sibling references in Swift. There's another kind of reference promoted by the Swift ebook, unowned, but I'm going to show you why it lacks the kind of safety you'd expect in Swift. An unowned reference is designed to point back to the owner of an object. It is weak in the sense that it does not change the reference count. In this case, owned class does not function properly without an owner object, for whatever reason. Since the owner reference is not weak, it is not an optional. Code involving it can be much simpler. It's also only ever referenced strongly by an instance of owner class. The idea is that owned class's owner reference will be valid as long as the object which owns it exists, and the owned class instance can't stay around for longer than the object that owns it. The downside is the owner reference is not safe. If the owner class object it points to gets freed and the reference is accessed, the app crashes. That's a heavy penalty for making a simple mistake, like letting a reference go into a multi-threaded context which just happens to complete execution milliseconds after the user has decided to move on to another portion of the app, destroying the owner class instance, thereby making the owner reference invalid. See, that was an easy mistake to make. In addition, the compiler will not enforce that no one else can get a reference to the owned class, and not enforce that all of its method complete execution before the owner is freed. In stark contrast to Swift's other flexible, powerful features, unowned stands out as a dangerous lurking corner, meant only to reduce optional operators and conditionals associated with safely dereferencing a weak reference. I highly recommend you do not use an unowned reference. Ever. Today we looked at reference counting as both time and graph problems. We saw what could happen if we created a retain cycle, and we learned where to use weak references. Lastly, we disowned unowned references. Automatic reference counting. Now that's Swift.